Hello everyone. If you can hear me, please put something in the chat. We are online. Okay, let's see. I still don't see myself. Oh, yeah, there it is. Excellent. So, my name is Ismael or Ishmael, if you prefer. You can also call me Snufkin. And the video today is intended to be a introduction to UXN. I have here a countdown. Let's do this for 1 hour. Okay. And let's start the countdown. So this is the first video for this channel, and the intention is to be reading documentation of several projects, some that I already used before, some that may be new to me, and share the journey. Like that is why the name of this channel is Docunautas or Docunauts, because we are going to have a journey across several projects documentation. Feel free to give me any feedback on the chat. And let's start. So I have left on the description of the video the URLs for the UXN wiki. Right now I'm here at the UXN website, and you can see this cute little drawing here. This is the UXN mascot. So let's start diving in. So the idea is that I read the documentation, but I'm going to be making commentary as well. So UXN is the virtual machine powering the 100 Rabbits software. If you don't know who is 100 Rabbits, let's go have a quick look at itch.io. They have several projects here. Okay. Rec and Devin, I think it's pronounced. Okay. Let's give it a moment. So basically they are a collective that creates games and audiovisual applications like this one. This is a game made in UXN, and it can be embedded here in jump with A. Oh, A is control, yes. So you can make little games like this, console applications, and many more things. You can see that it has this kind of retro style. I am very bad at this. Yes, there we go. And B should be out. And basically this is a very limited virtual machine, but we are going to check this out in a moment. So UXN is an attempt at crafting a comfortable bedrock for personal computing that is capable of hosting a variety of interactive graphical software. So it is mainly designed for portable audiovisual applications. There are some platforms that UXN is able to run on. There is a website called Awesome UXN where you can see all this information, and I'll make sure to add this to the description as well. It's here in GitHub. Awesome UXN. And here you can see that, for example, it runs on Game Boy Advance, Nintendo 64, Nintendo DS, and several others. Here we have in the documentation the UXN's instructions, reference, test Barbara devices. So the UXN is like the virtual CPU, and Barbara is a collection of devices that make the whole virtual machine. There we have several emulators here for Linux X11, SDL2, HTML5, etc. We are also going to see how to install UXN toolchain in Linux in a moment. So the virtual machine, programmable in Occidental, which is the programming language, is a portability layer with a focus on hosting graphical tools and games. It lives at the heart of the Barbara computer system and this wiki. So we have the official site and the community. There is a mailing list, a forum. We have a Discord server, and also you can come and chat at IRC on Libera Chat at the UXN channel. These illustrations are done by Rekha Vellum, which is part of the 100 Rabbits collective as well. And we have this very cool like aesthetics for the virtual machine applications, and these like caricatures, I think it's called. So we have design. We are going to look at this at some point. So this is the UXN mascot, and she's Varvara. So she has all the devices, and UXN is the CPU. Okay, so now let's go and dive into Occidental, the language. We go here at the top of the wiki. It's a little bit confusing if you don't know how to traverse this, but basically we are here at UXN, and here on the right is everything that stems from the UXN node. Now we are going to load the Occidental, and as you can see, we have syntax, stacks, and several others. So Occidental is a programming language for the UXN virtual machine. UXN programs are written in a stack-based flavor of assembly designed specifically for this portable virtual machine. TAL files are textual source files. ROM files are binary program files. Applications that transform TAL files into ROM files are called assemblers. Again, we have here design, cheat sheet, tutorial, a manual, and BNF notation, which we'll see at some point. So let's go with the setup here first. So it says here is a quick way to get started writing programs with a little self-hosted assembler and an emulator which includes the console device. Okay, let's just quickly see. Now we are at the Barbara. Here we are in Barbara section, and let's just have a look at what devices are connected in the Barbara standard. We have the system device, console, a screen, audio, controller, mouse, file, datetime, and then we have some unused space for more devices. Like you could create your own devices, and this is reserved in the specification, so it can still be expanded. Okay, now let me go back here. And let's try following these instructions. So these are the very first instructions in the documentation. If all these code examples that are underlined here, they are actually links. So feel free to explore that as well. We are going to run the first command. But before we do that, let's create a directory just for this. Oh wait, I don't think this is a good idea. Let me use this other one. Okay, make dir uxn cd uxn. I think this font is big enough. Okay, so now just let me see. Okay, now I'm in the uxn folder, and we are going to do everything here today. So let's open here this link, and it will take us to this uxnmin.c.txt. I'm going to copy this and wget this text file. Now I'm going to move this to just.c like this, and the command in question, oh, I'm sorry, it's muscle memory. Actually, I can change the... Okay, so let's run this command cc, which is the C compiler, cc, and I already have this command uxnmin.c with an output for uxnmin executable, and it's going to do its thing. It compiled in 4 seconds, and now if we list the contents here, we can see that this is the source code for the emulator, and this is the executable. We can open this .c, and as you can see, it is about 150 lines of C code. It is very, very small. Let's run this. We have to put ./uxnmin, and it tells us how we use this. So uxnmin, and we need to pass a ROM file with optional arguments. Okay. So let's see. The next step, we have already the emulator. The next step is to build the assembler. And the assembler is this file with hexadecimal. We need to convert this to binary. So again, I'm going to copy here and wget drifloon. I made a typo. Okay. And now let me move this to drifloon. I'm actually going to call it hex, because this is just textual data but with hexadecimal numbers. It is still not yet a binary. For converting this hexadecimal to a binary, we need to run this command. So let's do this. So xxd will convert from textual hexadecimal to binary, and the p option, I'm not sure what this does. Let's check this out. So p is for plain text, also known as plain hex dump style. Okay, so p is just telling xxd that this is plain text, and we are going to do the reverse from text to binary. The name of the file is drifloon hex, and we want to output a ROM file called oxnasm.rom, and it's done. Now We can inspect the oxnasum with xdump capital C for canonical mode. And this is our binary ROM. You can see on the right is the ASCII for each byte here. So you can see strings in the binary like this. Okay, now the next part is, I'm sorry. Okay, let's assemble the opsi test.tal. This is a file that is used to test a new virtual machine implementation. So let's download this one. And I'm going to move this to opsi.test.tal. So all these files have the txt at the end, because it is so that Devin, the creator, can upload this to this server. And we just need to change the extension. Okay, so now we have, if I open this, you can see that my editor has syntax highlighting for the source code. And now let's just run the command to convert this textual code to a ROM that can be run as well. So the assembler is a ROM, and this application is a ROM as well, and we are going to use the emulator along with the assembler to produce this output. So let me copy now this. So cat opsi.test.tal is going to read the file and output everything to standard output. Then it's going to be piped to the emulator, which will be running oxnasum. And then we are going to redirect the output to a file which we'll call opsi.test.rom. And this oxenmin needs to have the dot slash because it is not in our path. Okay, so it's taking some time. Let me actually okay, so this is just to make the computer a little bit faster. We also have an option here. Okay, that should help. Now we have the opsi.test ROM file, and finally let's run it and see what happens. So we are going to say /oxenmin opsi.test.rom, and as you can see, it just runs us several tests. It's telling us that everything is passing. So this oxenmin emulator is compliant with this test. Okay, so with this we can run the following code that is here. So let's explore the syntax, oxental syntax. In stack programming, there are no variables and no precedence rules. The calculations are merely performed in the sequence in which they are presented. The order with which elements come off the stack is known as last in, first out. In the stack AVC, the C item was the last to be added and will be the first to be removed. So it says 01 dop at 03 mol. What is this doing? Okay, let's think. Let's add here a readme in Markdown. So we have the uxn introduction 1. So the stack here, when we say hash 01, we are pushing the 01 byte into the stack. Okay. Then we can duplicate it and we would have 0101 on the stack. After that, the add opcode is performed and it will take these two elements, add them, and put the result back on the top of the stack. And then we are pushing a new byte 03, and then we do the multiplication 03 02 multiplied gives us 06. Okay, so the stack is last in, first out. Also, it will be mentioned, but the stack is circular, and we will add some more details about what this means. Right now, let's run this small snippet here that we have. So for this, I'm going to create a new file. Micro is my text editor of choice, but you can use any other editor if you want. Let's call this intro 00.tal, and we just say push the byte 1, duplicate it, add 1 plus 1, which will leave 2. So at this point, the stack will have 2. And then we push the byte 3 and multiply. And here we will have 06 at the top of the stack. Okay, so let's save this, quit, and let's run the command to create so it is intro, and the output will be intro 00. Okay, it only takes 7 bytes, and now let's run it. And nothing happened. Okay, so what's going on here? We need a way to actually see the results, because else it is going to perform the calculations and exit immediately. So to do this, we can see here in Barbara a specification we have in the system device. There is a debug port, which is 0E. This is the full definition of this device. But in order not to get more confusing that needed at this point, let's just define this as follows. We're going to put here 0E, and we create, this is the absolute path, and it's telling us that at this position we are going to create a label. The label is system/debug, and this is just to represent that is 1 byte. After using this syntax, we need to go back to 100 hexadecimal, because this is the start of the program. Okay, so this is a start of program, and then we need to call something that will give us the result that we have here. So in order to do that, we just need to push a non-zero byte to system debug and use this other opcode. So this stands for device output. So we are sending the byte 1 to the system debug port, okay, in the computer. Let me save this and let's run this again. Now we are using 12 bytes because we added the instructions to call the system debug port, and let's run it again. It is not working. Why? Let me see. What did I do wrong? So we're just adding this, multiplying. Oh, okay. So I think I remembered the min does not have a system debug port because it's min, it's very minimal. So this only helps us to, for example, if we would wanted to print something, we could define another port, 18, called console write, and this one is defined in min, and we can see, for example, dot console write do. This will actually print something to the terminal. Now let's run it. There we go. So it printed a star, okay? But I think that in order to continue, it is good to know that we can like bootstrap everything from these instructions. But let's go ahead and build a more capable emulator for this. I like to use the SDL2 implementation because it has sound, it has everything you could want to play with. There is another one for X11 that is faster, but that doesn't have sound. So just in case you want to try doing something with the sound and you're using another emulator and it doesn't work, it may be that the emulator actually doesn't support that device. So here I am going to clone this repository. As well, I'm going to add this to the description. It's in SourceHot and it's just called rabbits/uxn. So let's do git clone uxn, and this is going to download the repository. Now we change to this directory. Let's do a tree here. So it has a lot of files and demos, projects that you can also check out. But what we are interested at this moment is running this mk file, or no, this build script. Okay, so in order to do that, I'll just run build. Okay, so it created a command line interface version, a graphical user interface, and also an assembler that is called oxnasm. This assembler is deprecated, so we won't be using this, but we will use oxencli and uxn GUI. Okay, so we can see that this is like the default demo, and it is a computer desktop for UXN called Potato. We have we can create files and do things. Let's see if this build jump. Okay. So yeah, we can do some things. This is very good demo. We have a taskbar and everything. Let's exit and go back to the terminal. If we see now, it has created this bin directory. So what we are going to do is copy everything in bin to the parent folder, and then we are going to move to the parent folder. So now we have oxnasm, oxencli, oxenmin, and oxenemu. Let's do this again, but with instead of using oxenmin, let's just use oxencli. And there we go. We have the star here, and then when we call the system debug port, it will print the stacks in this fashion. So the WST stands for the working stack, and RST stands for the return stack. And we have here the result, this 01. This one here indicates the stack pointer. So we are at the first element, and this first element is 6. The return stack is empty. Let's try to modify this. Micro intro tal. Okay, so let's remove this line. We are going to leave this here at the end so we can see the result. Let's simplify this, and let's say we change, instead of 1, let's make 2. So 2 duplicated and then added, this will be 4. Okay. And let's say we want to multiply by 2 again. Okay, so this will be 8 on the stack. I save it, and then let's assemble this again and run it, and there we go. We have 08 on the stack. Okay, now let's continue where we left off here. Numbers in Octal are not decimal. That is very important because it is very confusing if you are not used to. They are expressed in hexadecimal, which means that counting goes like 1, 2, 3, 4, 5, 6, 7, 8, 9, then A, B, C, D, E, F, isn't it F, and 10. It takes some time getting used to, but don't worry, you'll get the hang of it. Okay, so yes, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, the usual numbers that we use in decimal. But then we also have A, B, C, D, E, F, and what comes after F is hexadecimal 10. So this will be 16 in decimal. Okay. Now, without further ado, let's dive into it. Okay, so we already have here a widget which we can run. So we can also use this, but I am going to also run these examples in the command line because that is where most of the time we will be probably doing some programming. Okay, so the following example program prints the phrase hello world by pushing the address to a label on the stack and iterating through each letter found at the address with a loop that increments the pointer until it reaches end of phrase, at which point the stack is emptied and the evaluation halts. Okay, let's see how this is done. So everything between parentheses is a comment. It says this is a comment and is ignored by the assembler. Click the run button to evaluate the program. select the next example with the drop down. Okay, so here we can select from several examples, and we can just click run. I don't know what is build. Oh, great. So build will actually save the ROM to our local. I hadn't seen this. This is great. So we have built, if you want to assemble this file and download it to your computer, it says here assembled in 30 bytes, and we can also run this file. It is giving us only the working stack here, and you can see it printed hello world, and when it finished, the stack was empty. So it was like in nominal state. The stack always starts empty, and ideally it should finish empty. Okay. We can also step through the program. So let's try doing that. You can see that at some point there will be the characters appearing. Okay, and if we click finish, it will just complete the run. Now let's copy. I'm going to copy this into another file. Let's say micro intro01.tal. As I said, all these in between parentheses are comments. They can be at the end of the line. They can also be before the text of the code. As long as they have a space in between whatever is inside the comment and the parentheses. Also, this, for example, would be an error. You need to have spaces or the beginning of the line. Okay. So, for example, if I do this and I try to assemble this file, so this is intro 1 and intro 1. It says comment open, something wrong at reset. Okay, but if I fix that, you can see that now it works. So it can be a little bit confusing, but yes, so please, we could also use oxnasm just to see what the previous assembler did. Intro 01 dot intro 01 dot rom. Okay, so it gives a little bit more information. Let's break this again by omitting that space, and you can see that it says comment incomplete on reset, and in this case it's telling us the line 17, which is also not correct. Okay, so this is line 5. But anyway, the oxnasm is not longer being developed. This other oxnasm, I guess this is going to be the replacement, and at some point it will just be called oxnasm. And remember that this file was called drifloon. These are the new assemblers that are written in Oxental. This oxnasm one is in C. Okay. So now let's see. Let's go back to opening this file. Let me remove this comment. So the first thing it's doing is pushing the pointer to the text. Okay. So we can see here we have this label called add text, and then we have the string data. So remember, strings, different from other languages, they are not surrounded by double quotes. They just start with a double quote. And then if you want to put a space, you need to put the actual hexadecimal value of the ASCII space character, which is 20 in hexadecimal. And then we end the string with a null byte or a 0 byte. Okay, one thing that I like to do is make some macros for this, but I'm not going to complicate this at this point. So you can see that we have two labels. We have at while and at text. This dot comma is getting the address of where the first character, capital H, starts in memory. This will be something like, I don't know. Actually, we can like force this to be at a specific address. Let's say we have this, we want this at the middle of memory at 8000 hexadecimal. And remember, we will see in more detail later, but UXN has 64 kilobytes of RAM. So this would be right in the middle. And again, if we want to see what is the value of this operation, we can introduce macros here. Yeah, I guess it is worded. So the syntax to define a macro is like this, with a %, the name of the macro, a space. We can actually have here a comment. For example, this is a fourth style comment. This means that this macro doesn't take anything from the stack and it doesn't put anything in the stack. Okay. Let's see now. We wanted to push byte 1 to system debug and then output that to that port. We also need to define this system debug label again. So that was in 0E system debug and it's 1 byte. And what we are going to do now is, after this text, let's put debug. Okay. Then we save, quit, and let's assemble this again. Writing in 0 page. Okay, I forgot to put this here again. So remember, every time we define a constant or this kind of symbols, and we use this syntax, we have to return to this address, which is 256 decimal. This is where the program actually starts. And the error says that we are trying to write in 0 page. 0 page is the first 256 bytes in the RAM, and then we start here. Okay, so each page is 256 bytes. Okay, this is also called like page program. I seen page program, or it could be also like page 1. Okay, so before this is page 0 and this is page 1, where the program will start. Let's try assembling this again, and now let's run this. So now it's way bigger because remember that I moved the string to the middle of the RAM. Okay, we can inspect this again using xdump, capital C, intro1 ROM, and we can see that this is the actual bytecode. Then we have from this address to up to this one, we have a lot of zeros, just spaces, and then we have here our hello world. Okay, this is the string. So now let's run this again. Oh, but they want 0, 1. Okay, so let me split this. So remember, we put this at address 8000 hexadecimal. So we have here 8000. So when we say semicolon text, we are pushing to the stack this address. Okay. So in this case, it is 8000 because that is what we put here. If we don't put anything here, it will just be whatever the address is after this code. Okay, so let's try this. And I am going to add to this command dot oxencli intro01.rom. Okay, so that we can just make this in one command. So it assembles to 37 bytes, and now the address is 0117. Okay. Then we go to the while, and it is going to start with this opcode load absolute without consuming this address. Okay. Then it's going to duplicate whatever it's there. So let's move our debug after here. What I did is suspended, press Control Q. Okay, I don't know what I did, but okay, so we are going to move the debug macro here to see what happens when we run this opcode. And let's just, now we have several of these being printed because we are inside this loop. Let's see the first one. So first we have the address of the string, and then it will load the byte at that address. So the first byte is H. Okay. We can check what is the value, like echo H, and we send that to xdump C. We can see that it is the byte is 48 for the capital H. Okay, so that's what this new byte here represents. So now we have the byte for capital H. Now it is going to duplicate it here. Okay, so we go back here. So we have 0117 48 48. And remember, when I say 48, all this is in hexadecimal. I just say it like that because it's easier. But it's 48. And then we have this syntax here. Let me make this bigger. This is a test. If this is non-zero, we will jump to this label, anonymous label here. So these curly brackets, they are just like this ending one is like any other label. And if this is true, it will jump here. If this is false, then it will go back to this part. So since 48 is not 0, it is going to jump here. Let's see now, before the DEO, let's put debug here. And let's run this again. Okay, now we have the second 48 was consumed during the during testing of this. If this is 0 or is 1, then we jump it here and we push 18. And remember, 18 is the port for the console write that we used before. You can see here in the barbar specification, console write is 18. Okay. So we have seen previously what this does when we use DEO on this port. We could also change this to .console write if we wanted, and we just need to define that here. 18 at console write, and it will be doing exactly the same thing. Okay, so once we print, and you can see that after this we printed the capital H here, and then it continues. It says he L L O, then a space, and then world. Okay, we can remove the debug. We need to save this, assemble, and run again. Okay, so it's working the same. Remember that this .console write is just the same thing as pushing this byte and then applying this this opcode to this port, and we have the letter H on the stack that will print capital letter H, and then we increment whatever is after the so when we run DEO, this will be consumed and this will be consumed, and it will leave only the address again. We can check that after DEO. Okay, you can see that after printing the H, we are back to the same address, and then we are going to run this opcode increment 2. So this this K means that we don't want to consume the arguments, and this 2 modifier means that we want to treat these 2 bytes as one value, as one bigger number. And you can see that after we run this, it will increment the address. So in the first iteration it is 17, the second one is 18, then is 0119, and so on until the last one. So this last character here, the exclamation mark, is in 0122 address. After we do that, it will jump back again to the while branch, and that is how this loop is implemented. So how do we exit this loop? If we find this null byte, this test will fail. We will not be jumping here, and then we will continue inside these curly brackets. So let's see what happens when we do that. Let's put a debug here, and Let's remove this one. Okay, so if we run it again, you will see that it prints the full string here, but then the byte that is loading with this command is 0. So since this is a 0, it will be consumed, but by this, let me see. Oh yeah, so we duplicated here the value to test it. And since we are at the end of the string, we want to finish this. We are going to do a pop to remove this 0 byte. Then we are going to do a pop 2 to remove the address. Okay, cleaning the stack. And after that, we are going to break, and this will end the run. Okay. So we can check that at the end, the stack will be clean again. Sorry, it needs to be here. Because after this break, the debug was ignored. So we put it here. And yes, we can see that after printing the string, everything is back to normal. The two stacks are empty, meaning that we did everything correctly. And now let's just remove. Oh, let's just put one at the beginning, and again this one at the end. Why it's not saved? So this again needs to be before the break, Ismail. Okay, there we go. So it starts empty and it ends empty. Let's say we don't we forget to do this. Then you would see that after finishing this, it would still have the address of the last character. And in this case, I mean, there is no issue. It already did what it needs to do, so you can leave the stack dirty. But normally you want to do something after doing whatever you were doing, so you just need to keep track of these values and clean properly after using them. Okay, so I think it's almost 1 hour that we have spent with this. This is the first video I do of this kind. If you would like to give me any feedback, I would really appreciate it. I don't know if you felt it was too fast, too slow. I do want to do this as easy as possible for everyone that has the interest to learn this. So if I have skipped some information or details that you do not understand, please leave a comment or visit us at the IRC or the Discord server. Again, remember that is in Awesome UXN. At the very end, you can see where it was. Here, community, and you can see, you can just click here and it will open a new well, this is not a new tab, but anyway, you can put here, like for example, I want to say I am full, and you just click here connect. Oh, already in use. I bet no one is full, like this. Yes, there we go. So it will automatically connect you to the IRC channel of UXN, and you can start typing messages here. You can see there is a lot of people that is part of the community. Currently there are 103 users here, and you can also set up something like I use Quasel IRC, and you can see here we just this is the what we just did before in the browser. Here it's connected and then disconnected. Okay, you can find me here as Snufkin PC, or sometimes it will say a Snufkin laptop or a Snufkin phone. Let me see. Okay, so that's it for today. Let's just do a quick recap. We explored the wiki, we built our toolchain, and we ran the first hello world. Remember, you can also run it here directly if you don't want to do this part just yet. I will leave all the links that we opened here in the description as well. And in the next session, we will, instead of continuing this, I would like to read more, because this keeps describing the first example. Okay, but that will be in another session. I plan to do this 1 hour long, and once we finish that description of the hello world that is here in the wiki, we can go back and explore the other examples. Okay, I'm also going to try to streamline my setup here, because I typically use this, but please tell me if you think that this is not pleasant to see in the recording. Let's see, for example, if I change here, micro intro 01.tal. It never does that. It's very weird. Oh, intro. Yeah, I guess. Oh, I guess it is because I am streaming that is like slow. Yes, because if I'm not streaming, it doesn't look like that. But anyways, I'm going to make sure that next time I just use this other one. This is called Yakuake, like this. Yakuake. And I just like that it pops in and out from the top like this. If you have any other question, just please let me know. And with that, I'll just say goodbye for now, and I will prepare the next session probably tomorrow, or probably even tomorrow night. I mean today at night. Let's see how much time I have available. But anyway, I'm going to put notice on IRC at least half an hour before the stream starts. And with time, I will try to plan them more with greater detail, and with more time in advance before the streams. So thank you for watching, and have a great day.